Assistive robots have the potential to help people perform everyday tasks. However, these robots first need to learn what is it that their users want them to do. Here we can see a user trying to teach their robot to carry a cup upright. But because of their inexperience, even their best demonstration accidentally tilts the cup. So how do robots learn from these suboptimal demonstrations? Current methods often ignore the human's limitations and assume that every user can provide any demonstration. Our insight is that inclusive learners should give human teachers credit for their limitations. We proposed an algorithm that compares the human's demonstrations to similar and simpler alternatives. Here, we test this algorithm in a user study. Let's start with the coupling task. The user wants the robot to deliver a cup without spilling its contents. Here we show the optimal behavior that the human wants this robot to learn. On the left, we show an example user demonstration. In the middle, you can see what the robot learned, and on the right, we plot regret. Regret captures how much worse the learned behavior is compared to the desired behavior. Here, the robot learns with Bayesian inverse reinforcement learning, a baseline method that ignores humans' limitations. This robot learns to match the human's demonstrations and also spills coffee on the way. Next, we learn from the human's demonstrations by comparing them only to similar alternatives. These are produced by noisy perturbations to the trajectories. This robot was uncertain about what the human wanted. Finally, comparing the user demonstrations to both similar and simpler alternatives helps the robot extrapolate the human's objective. This robot minimizes the average regret across all users. Next, we tried a precision task. In this task, the user wants the robot to stack a marker on the box. Because the robot's motion was noisy, users could not stack the marker in their demonstrations. As before, the BIRL robot learned to mimic these demonstrations and also did not stack the marker. When the robot compares the human's behavior to noisy alternatives, it's still confused. The robot thinks that both stacking the marker and dropping the marker could be what the human wants. But when the robot also compares to simpler alternatives, it extrapolates the human's true objective. Again, our approach resulted in the lowest average regret across all participants. Finally, the users completed a constraint task. In this task, the user is attempting to drop some waste in the bin by reaching around an obstacle. Because users were constrained to control only the robot's position, they struggled to manipulate the arm around the vase in their demonstrations. The BIRL robot learned to mimic these demonstrations and also moved directly to the vase bin. As before, the noise baseline is overly cautious. This robot is not sure what the human's demonstrations are optimizing for, and thinks either moving through the vase or around the vase are equally likely. The robot only learned the right thing when it reasoned about similar and simpler alternatives. Overall, these user studies suggest that our algorithm enables robots to give human teachers credit for what they cannot demonstrate and learns what they really meant.